Good afternoon, everyone. We're going to go ahead and jump into Big Idea 1, Part 1. Now, notice it said Part 1. We're really going to break this up into 3 separate parts. First part is going to deal with the atomic structure and periodicity, periodic trends, and the structure of the atom, those types of things. From there, we're going to build, and then we're going to talk about how we can probe the inner structure of the atom, even though it's so small that we can't physically manipulate it. Then after that, we're going to jump into some familiar and some people's not so much favorite thing, which is talk about some stoichiometry as we continue on. Now, we'll be on this entire unit, we'll say probably about close to a month. So we're going to spend a little bit of time here, but I want to make sure that you are practicing, you're keeping up with everything, working on those practice problems and homework problems that may come up. Let's go ahead and jump in. Our learning goal is going to be the same learning goal for the entire Big Idea 1. Students will understand that chemical elements are the fundamental building blocks of matter, and all matter can be understood in terms of the arrangement of atoms. These atoms retain their identity during chemical reactions. So everything is going to tie back to this. So whether we're talking about the structure of the atom, whether we're talking about how we probe the structure of the atom, or even dealing with stoichiometry, everything is geared towards this one goal. So we want to make sure we stay on target. Now, first part, from electromagnetic radiation to Bohr's model. As we look at the picture here, we notice that we have all these different color fireworks, and we enjoy seeing them every 4th of July and just whenever we get a chance to send these off. So, why do we get colors, and why do different chemicals give us colors? We're gonna start off talking about light and how it behaves, and we're gonna slowly move towards Bohr's model that'll help us to get a better picture of these answers. Now, when we deal with light, of course, we deal with 3 main things. We deal with wavelength, frequency, and speed. All of these are shown to us based on the characteristics we see on screen. Wavelength, many times being shown to us as lambda, frequency as nu, that's not a V, it's nu, and the speed, which is speed of light, 2.99 times 10 to the 8th. Many times we'll deal with it as just 3 times 10 to the 8th, which is just fine. We're going to look back at this formula here because we want to realize that whenever we multiply our wavelength times our frequency, it's always going to end up being the speed of light. Every single time. That's going to be a constant. Okay? Now, as we look at the diagram here, we see the different sizes of the waves. We go from 4 cycles per second, more wide strokes in terms of our wave, and we make it more narrow, we get more cycles in per second, or increase the number of hertz that we're going to actually be looking at here. This is going to play into how we actually classify our radiation, our electromagnetic radiation. Looking at the shortest waves coming down here to the end of the spectrum, our gamma rays having very, very short wavelengths, but very, very high energy, moving all the way down to our radio waves, which will have much longer wavelengths, much lower energy. And right here, not really in the middle, the area of light that we can actually see, or this type of radiation that we can actually see, going from about 4 times 10 to the negative 7th meters to 7 times 10 to the negative 7 meters, which is, if we look at it, nanometers would be the best way for us to do this. Now, what I want you to understand, and hopefully you see this as we look at this, each one of these colors is represented by a wavelength. You cannot forget that. So when we start to talk about how things change and with Bohr's model, you want to remember that there's a number and a color tied to that wavelength. Now, how does Bohr's model actually relate to this information we just covered? Well, we know that according to Bohr's model, he had the idea that the electron just travels around in the circle, this nice clean orbit around the nucleus. And he did all of his studies and all of his information based on hydrogen, which makes perfect sense. It's the simplest one to deal with. Now, at any given state or any given time on a normal day, the electron was found at what we call its ground state. That is going to be the lowest possible energy state, or N equals 1. We know that N stands for our energy level. So you want to make sure that you're paying attention to those little parts. As we look at this diagram here, we're starting to see that the light which our energy was sent through, the hydrogen gas 2 through the prism, and we began to get these separate lines. Each of these lines is representative of some information that we've already covered. What do I mean? Well, if you notice the distance between each line and the fact that they deal with a specific wavelength, this is helping us to see where these electrons are actually located and which energy level we're dealing with here. So, again, that's why I said make sure you remember there's a color represented by each of these numbers. Now, as he started to hit these electrons with energy, he would note that they would go up to a different energy level. As they would come back down, that energy has to go somewhere. It can't just stay where it is. So, depending on how high it went up, that would also tell how much energy it loses. That energy would then give off a specific color. That lets us know, one, where the energy is actually organized, but two, what wavelength it is that we're dealing with. We're going to do some things in class that will allow you to see this a little bit clearer. So if you're freaking out about this, don't worry, calm down. We will get you there. Now, some may ask the question, okay, well, Mr. Baldwin, what about what's happening here? Notice that we have all these lines here, but they're not showing up in any color. They all just look black. Now, this is where we're dealing with electrons of much higher energy levels. This means, if we can't see it, that it falls outside of that visible spectrum that we're dealing with on a regular basis. But depending on how close, this one went up to 2 and came down, gave off a little bit of energy, we had a red line spectra. Went up a little bit higher, green, and eventually up to blue. Now, Bohr took the time to actually calculate out all this information using the following formula. This representing the energy that's lost, and then the distance that multiplied, by the distance that it actually fell. We're going to use this in class to calculate the energies of each of those levels and see which wavelengths and why each wavelength is where it is. Now, everything up to this point seems like it's working. Bohr's idea is right on par and everybody's loving it because it tells us that, we actually do have these quantized energy levels and that the electrons have to actually make it to those levels. Wonderful. We look here and we see that Bohr's model was actually incorrect. Why was it incorrect? Well, Bohr's model was very nice and neat when we dealt with hydrogen. It only has one electron to account for. But once we began to add more electrons, things began to fall apart. So this is where we're going to start to transition into our next section, which is looking at the quantum mechanical model and Schrodinger's input and de Broglie and all these guys and how they impacted our current understanding of the model and how we can use that information. I hope that you find this helpful. Make sure you're filling in the information for your guided notes, and I will see you in class tomorrow. Have a great day.